sure you bring your calculator next week for the test. So there you go. So. I hope that doesn't come up Japanese or something. So it's 75.79 squared. Okay, I squared times, which resistor do you want to use? First one, 200 times 200. So that gives you 1.148 watts. Got it? I'm going to go over this.
Does that run?
Yeah.
No, I don't do these two.
Well, so you want to know, so you've got that much power being dissipated by that resistor. So you just want to pick a resistor that is the next highest rating so it doesn't blow up. So if, like for this guy, it would be like 5 watts. See that? See that?
So this.
Yeah, yeah. And for this one, it would just be 2 watts. There you go. Okay, let's do this first circuit. And I want to show you some stuff. There's a lot, simple circuit, but there's a lot going on. Okay, before you get into the second one. So the first thing we note is that these guys are in series, and by definition, components are in series when you have the same current flowing through the the loop, the components, as opposed to something like this. If you had resistors connected like this, for example, and you had a battery there, so the current would be the total current would be flowing in that circuit up to this point. And then something happens here. Some of the current's gonna go this way, some of the current's gonna go that way. When that happens, when you have different paths, those components are said to be connected in parallel, all right? So these guys are in series. So that means whatever current is coming out of that battery, it's the same current going through there and there. Same, okay? Now, if I want to know I've read that current from my multi-sim circuit as 75.789 milliamps. I want to know, just for fun, how much power is being provided to that circuit by the battery. So we know the voltage and we know the current. So the power is 72 volts times 75.789 milliamps. Which is, milli is 10 to the minus 3, okay? So if you multiply that out, you get 5.456 watts. Now, I don't ask for that in the lab, but that's what you get, 5.456 watts. And notice what formula I used. I used the voltage and the current, because I know both quantities. And quite frankly, for an ideal power source, there is no resistance, so you almost have to use those two. Now, I'm asking how much power is dissipated in each resistor. And then the third part, based on the power dissipation, what kind of resistor would you choose so that the circuit doesn't blow up? So let's look again. We know the current, 75.789. The power dissipated by this resistor and this resistor, in order to find that, you need to know the parameters that apply just to that component alone. In this case, we know that the current flows through both resistors and back to the source. So we know the current. And we know the resistor, so the power for that resistor is I squared, the power equation is I squared times R, which is 75.789 times 10 to the minus 3 amps squared times the resistance, which is 750. Power is equal to I squared R for that component alone. And that comes to 4.307 watts. Okay? By the same token, the power for that resistor is equal to I squared R. And that's equal to 75.789 times 10 to the minus 3 amps squared times 200. And that comes to 1.148 watts. Okay, so if you add 1.148, that's the power dissipated by that resistor, and 4.307, you should get this, 5.456, or close to it. You might want to check that. Now notice that here I used power equals voltage times current. Here I used I squared R. So, you know, everything will still work out. Doesn't matter which equation you use. Let's just say I gave you a problem and I said the voltage that is dissipated by this resistor is 3.2 volts or whatever. Let's say I just gave that to you, then you could use V squared over R, because those are the two parameters that apply just to that resistor. I'm going to take this one more step. So there's a lot going on in a little circuit like this. Do you remember the last time I said that there is this law called Kirchhoff's voltage law, where the voltage rise that is provided by the source, the increase in voltage as a result of the source, is equal to the sum of the voltage that is consumed by each one of these elements. All right, so the voltage by the source is equal to the voltage dropped across R1 and R2. Remember that? You can't have more energy. Whatever energy is provided by the source has to be dissipated by the elements in that circuit. If you had any energy left over, you could funnel it off into another circuit, and then you could do that over and over and over again and create a perpetual motion machine. All right? You end up with a power plant. And you can't have more energy being dissipated by the resistors than is being provided by the source, because that energy has to come from somewhere, right? So those two have to be equal. The amount of voltage that is provided by the source, the voltage rise is equal to the amount of voltage dropped across each one of those elements in the loop. If there was a third resistor here, it would be plus VR3. But there isn't, there's only two. So this is known as Kirchhoff's voltage law. Now, let's figure out what the voltage is across each one of those resistors. The voltage that is dropped across each one. And then when we know that, we'll go back and double check our equations, but we'll use this guy for the power, all right? So from Ohm's law, how do you do it? From Ohm's law, voltage is current times resistance. So the voltage across this guy is equal to the current through that resistor times the value of the resistor. The current is 75.789 milliamps. This is times 10 to the minus 3 times 200 ohms. So the voltage across that I don't have my calculator. Somebody multiply 75.789 times 10 to the minus 3 times 200, and tell me what that is.
15.157.
How much?
15.157.
15.157. Okay, so that's how much voltage that guy drops. Now let's do the same thing for this resistor. Voltage is equal to 75.789 times 750. What do you get?
56.841.
56 point what?
841.
56.841 volts. Add 56.841 and 15.157. I hope you get 72, we're close to it.
71.998.
71.998, 72, all right? So you see what I did? I just used Ohm's law, V equals I times R. I know the current through that loop, and I know the value of the resistance. Voltage is equal to the current times the resistance. And I did that for this resistor and this resistor, and that gave me the voltage that is dropped, the voltage that is consumed, I guess you could say, across each one of those resistors. Notice that the lower resistor, the smaller the value of voltage drop. But when you add those two together, as Nick just did, you're going to get 72. All right, now that we know the voltage across that resistor, and we know the value of the resistor, so let's use this number and this resistance with this formula and see if we get the same power that we did before. So power is equal to V squared over R. Power is equal to 15.157 squared over 200. And what does that come to? I hope it comes to that. Can somebody do that calculation? It's 15.157 volts squared over 200.
1.14.
1.14, is that what you get, Nick? Oh, you're just using the computer.
1.14. Yeah.
1.148? So it really doesn't, you can just kind of go in a circle with these equations. It really doesn't matter which one you use. But when you do use them, you need to know which parameter applies to which component. You can't find the power dissipated by that resistor by using 72 volts. It's just not gonna work. Not for a series circuit, okay? For a parallel circuit, the rules change a little bit. But look what we've done. This is a fairly simple circuit, and we've got the, just from looking at the meter reading on multisim, we were able to come up with the power, the voltage drop, Ohm's law, all that good stuff. And if you just, when you start to tackle a problem, you just say to yourself, okay, what do I know? where's my starting point? What parameters do I have? And what equations can I use to solve the circuit? If it's power, well then you gotta use one of these three. If it's Ohm's law, one of the three Ohm's law equations. Okay? If I give you a problem that says, and I say, okay, this is 72 volts, that's 36 volts, and I say, well, what's the voltage drop across this? Well, you know that you're gonna have to use Kirchhoff's law, 72, 36, that gives you the answer. You just subtract one from the other. Okay? Now go ahead and try to do, if you haven't done so, go ahead and do number 2 in that lab. And then we'll go over that guy. Oh, I added a resistor. Okay. So it's just more of the same. Tonight, this guy, and I'll send you the other two things. But another sheet. You have that one, but you don't have the lab. Oh, you will? I'll bring it in then. Okay, okay, see you.
Able to build that circuit? You got it? Good deal, good deal.
was the value of the current that you got, Zach, on that from multi-sim?
104.348.
Milliamps? Milli.
Yeah.
Ready to go over this? Ready? Okay, all right. Another resistor. So let's just, I always start with some, just by writing down some of the formulas. That means if there's more resistors, there's more voltages, okay? So those are the three parameters that we've discussed so far. And like I said last week, if you know this form of Ohm's law, you can just do algebra and come up with the other two. Okay? So you really, there are three forms, but if you know one, you can derive the other two. Same way with power. Okay, so what am I asking? Okay, we have the current. I want to know the power dissipated by each resistor. Again, this is just an extension of the last one. We know the current through each resistor, since they're in series, and we know the value of each resistor. So the power dissipated by R1 is equal to 104.348 times milliamps, which is times 10 to the minus 3 amps, squared, power equals I squared R, or power equals V squared over R. Squared times 150, and power equals I get 1.63 watts. Is that what you get? Or not? 1.633 watts. Okay? Power in R2, again, I squared times R. This time it's 550. Start over. 5.988 watts. That makes sense? Okay, now power in the third one is 104.348 times 10 to the minus 3. We're going to square that, and we're going to multiply that times 450. And I get 4.899 or 4.9 watts. And so the total of those three are, I don't think I asked this, but the total power dissipated, it'd be the sum of those guys, so that's one 12.52 watts. And just as a check, I'm going to calculate the wattage by the source, and that's equal to V times I. Power is equal to 120 times this. Which is 12.52 watts. So, again, I'm asking if you have some standard power ratings of resistors, 1/10, a quarter, 1/2, 1, 2, 8, 5 watts, 8 watts, whatever. What are we going to need? For this guy here, for the 150 ohm resistor, we're going to want to put a 2-watt resistor in there, 2-watt power rating. So we know that doesn't blow up when we turn the circuit on. For this guy here, is there a 6-watt resistor, or does it go to 8? Does it go to 8? I never remember that. So that's 8 watts. We'll want one of those guys. And for that resistor, 5 watts going to barely make it. I think 5 watts is the standard. So in this tray of resistors, we were playing with these last week. This is like 1 watt. See that little guy there? That's like 1 watt. And this one here, a little bit bigger, that's a 2 watt. So 8 watts is, you're getting a fairly large device there. And when you have resistors that big, you don't just jam them into a circuit board right next to everything else, because it's going to heat up everything else around it like a toaster. So if you put a 5-watt resistor in the board, now you need a little bit of space around it. So your equipment gets big pretty fast. And then, like on these power supplies here, they got fans on the back and all that good stuff. Much of what's inside of here is just to keep the thing from blowing up. Okay, now I could calculate the voltage drop across each one of these. We did that before, but I'll save that. This is actually we're a little bit ahead. We're in chapter 4, and we're going to go through that again in 2 weeks. So, but you're a little bit ahead of things. So I won't go through it now. What we're doing here, not on the test. Okay, it's a little bit ahead. This is mainly a multi-sim exercise. I want you guys to get more and more accustomed to multi-sim, because we're going to be doing a lot with that. It's kind of fun. But you'll have to know all this stuff here. The Ohm's law, the power equations, Kirchhoff's voltage law, very basic stuff. And on the test, when I ask you for Ohm's law, it's just going to be one resistor, like that. You won't have to worry about the series calculations. Okay, who has questions? Is it kind of making sense? If it isn't, it will, because we're going to go over it again. And the more we do this, and the more you play around with it on the computers and see what happens, and we start building circuits and you hook it up to the power supplies and see what happens, it's just gonna start making sense after a while. Okay. Turn in everything that you've done so far. Let's take about a 10-minute break. And I have a review sheet of stuff. It's scientific notation, engineering notation, a couple of calculations, identifying resistors by the band color, and two problems on resistivity, which we've all done before. I just want to wrap everything up into one package, and that will be it for this evening then. So go ahead and take a 10-minute break, and then we'll finish up. Oh, thanks. Okay. Got my stuff all over the place. Thank you. Thank you. Yep. Is that everything then? Okay. couple of little tidbits just from last couple of classes. Is that direct current or alternating current?
And that's, all.
What was it?
Is it direct or does that curve represent, voltage? Does that curve represent direct current or alternating current? Direct current, okay, remember that? Because there's nothing below the line here, nothing. So the current's only going in one direction, okay? Here's the representation for alternating current, like so. This is time. So the current here on that part of the curve is going one way. Current here going the other way. Electrons are going back and forth, back and forth. Remember that? Okay. I can't tell you how many people just are so confused by that. So if I were to start out with this curve, and that's alternating, and I were to change it to direct current like you would find in this power supply where you have direct current coming out, the first step would be to get rid of these guys here. And you would do that by creating a circuit called a half-wave rectifier. So that waveform is direct current. It's 1/2 of a sine wave, but there's nothing here. Nothing. So the electrons are only going one way, okay? Another little tidbit. I'll just ask you a question. By convention, do electrons have positive or negative charge?
negative.
Negative charge. Electrons, by convention, is always negative charge, okay? And then, this is a little bit confusing in your book on page 8, right at the beginning, it talks about the types of circuits, active and passive, and it mentions on page 8 that there are 3 fundamental passive devices in the entire industry. There's only 3. We're studying one of them. And resistors, capacitors, and inductors. It says in the book there are 3 fundamental passive devices. And it lists those 3. And then it goes on to say, well, there are other passive devices, but the other, in that second sentence, the word fundamental is missing. I think it talks about diodes and transformers and all that. This is the key right here. 3 fundamental devices. So whenever you design a circuit, for those of you in electronics, if you want to model a transistor, for example, or model a transformer, a little bit more complex devices, and you want to create a mathematical model, a circuit, a model on, let's say, multi-sim, you're only going to have resistors, capacitors, and inductors in that model. And you also have current sources and voltage sources. We drew a battery, which is a voltage source. But that's it. I don't care how complex the circuit, those are the 3. So these guys, and the reason is there's only 3 ways to store energy in an electrical circuit. The capacitors store energy in an electric field, inductors store energy in a magnetic field, resistors don't really store energy, but they operate on electromagnetic energy. So as soon as you put current through a resistor, it heats up, gives off heat, which is electromagnetic energy. So this is electromagnetic. This is electric. and that's magnetic. And that's the only reason you have three. Okay, three fundamental types of components. Remember, anything that's above the line like that, no elements below the line, direct current, may look like alternating current, electrons have negative charge. Okay, does anybody want me to go over scientific notation? You want me to do anything with that? How to convert scientific to conventional, conventional to scientific? Because that's what's on this sheet. If you get to one you don't understand, let me know. I'll go over it. But I'll be glad to do it now. Are you guys good? Okay.